Okay, we're going to finish up chapter 5 today. We've got 5, 6, 5, 7, and 5, 9 to play with. I'm going to go through them step by step. Some of them are right from the book. This 5, 7 is not going to be from the book, so we're going to vary from it a little bit. Okay, we started out with designing the beam. Remember the last lecture, we ended up with a 3 by 16 based on stress, the bending stress. And now we're looking at making sure that the rest of the parameters that could fail and cause us a problem are okay. So the first one is shear. So that's going to be 5.5. S-H-E-A-R, shear. Okay, this is the equation you guys hopefully remember. Okay, that is the equation. Look in the book. If you're on page 207, you've got this equation. I don't know about you, but if I look through my glasses, those things don't even appear to be even close to each other. This little FV is there. This V is there. I don't see anything else that even comes close. Okay, you got to know why. Why does this work? Okay, it works because what is lumber? Lumber is a rectangle, a 2 by 6, 2 by 8, 2 by 10, 2 by 12, 4 by 4, 4 by 8, 4 by 10. It's a rectangle. So I'm going to draw a rectangle on the board. And if you go to your book on page 666, you're going to see this rectangle, okay? So 666 is in the back of your book, of course. And if you go to that page, you're going to see in the top left-hand corner is a rectangle. And it's got B and D written right there. B is the width, D is the height. B is the width, D is the height. And it's also got an equation there. It's got I equals BD cubed over 12. Okay, this relates to that. Okay, I'm going to show you why this equation is this equation for one special case, a rectangle. Okay, so let's do it. I'm going to put FV equals VQ IB. Okay, what are these guys? B is the width. That's a good, I'm going to leave that letter right there. I, B, D cubed over 12. V, I'll leave that letter right there. Okay, Q. We just did this not too long ago. What I tell you to do, find the neutral axis. What is the neutral axis of a rectangle? In the center. So I'm going to draw a line right here, and we're going to take that, we're going to put this as D over 2, D over 2. Definition of Q. Crosshatch the top or the bottom. Take your pick. And take the first moment of the area about the neutral axis. So Q would be the area. Is B times D over 2. That's the area. And the distance to the center of that is right here. It looks like D over 2 divided by 2, which is D over 4. So there's the area, there's the arm. So if I take that and run it through, it's BD squared over 8. Come over here, BD squared over 8. Okay, I'm going to do a little bit of math here and see if we can get to where we want to be. So I've got this mess. Let me see if I got it right. I'm going to save the V. I like it. I'm going to leave it by itself. It's a good thing. Okay, now, how do I do this mess? I think I flip and flip. So I'm going to flip and flip. BD squared over BD cubed 12, 8. Okay? Hopefully that equals that. And I got another B at the bottom here. So I got another B to worry about. That one. So I flipped and flipped. Now I've got 12 BD squared divided by 8 BD to the 4th. No, I lied. B squared D cubed. That look better? Okay, what can I do there now? I think I can put the 12, and the V is still here. The V. I'm going to move the 12 out in front and the 8 underneath. That takes care of this part. Now, I'm going to get rid of one B here and one B there. That makes that a B. I'm going to get rid of two D's here and two D's here. That makes that a D. So now I've got 12V over 8BD. What is B times D? Isn't B times D the area? So this is the area. So now I've got 12V over 8A. Can I take and divide 8 by 8 and get 1, and 12 by 8 and get 1.5? And doesn't that come close to matching this? Which is exactly the same equation if I specialize it for a rectangle. So that's how you got that equation. Much easier. Now if you got this shape, and you use that equation, you're playing in the wrong ball game. That equation is not meant for anything but a rectangle. Okay, that's what it was designed for. So there's our equation. So let's do a couple problems, and then the rest of this is pretty simple. Okay, let's figure out what we need to do here. I got 5.5a. If you want to start looking at it, be my guest. 5.5a, we're going to do 5.5a and 5.5c. And I'm going to get this, I'm going to leave that right there. Get rid of all this. I might as well make it nice and fresh. So, big FV, it's got to be greater than or equal to okay, let's do it. We're not going to be long now. This isn't going to take us very long. So go to 5.5. Look at the problem. See what it says. 5.5, where are you? There you are. I am on page 208. It says I got a 10 by 10 beam. Select structural. Doug Furlarch. It says right above, note the following problems are Doug Furlarch. Neglect the beam weight. Structural supports a single concentrated load of 10 kips at the center of the span. Investigate for shear. What they want to know by saying investigate is the actual less than the allowable. Is this the case? So I go to page 114. Take a look at the little picture. It says if it's L over 2, the V is P over 2. V is the maximum shear. That's this letter. So it says for this particular case, V equals P over 2. 10,000 divided by 2 is 5,000, so 5,000 goes right there. And it's a 10 by 10. So where do we find all of our properties? Back of the book, 676, 677. A 10 by 10, how big are you? 10 by 10 is 90.25 square inches. Do the math. 1.5 times 5,000. 1.5 times 5,000 divided by 90.25. 83.1 psi. Okay, where do I get the big FV? Always, bigs are tables. So let's go to the table. And when I'm at the table, I'm going to find a 10 by 10. It's a beam, cell number 2. And I'm going to find select structural. Second one down, and I'm going to go across. And when I get FV, I hit 170. So this side is 170. Is that a true statement? Is 170 bigger than 83? Yes, it is, so it's okay. Okay, the second one. Get rid of this, this, and this, and this. Second one. And I might as well get rid of this. .5C. Okay, let's see what it says. It says I have a 10 by 12 beam, number 2. Eight foot long and has a concentrated load of 8 kips, 3 foot from one end. 8 foot long. Okay, that looks like something I could do with the table too. If I go to case 7, if I want V, I take P, B over L where B is greater. So V equals P, B over L. 5,000 pounds, that was case 7. 5,000 goes right there. What's the area of a 10 by 12? Back of the book. 676, 677. 10 by 12 has an area of 109.3. Do the math. Check the table. 1.5 times 5,000 divided by 109.3. 6862. Go to the table. It's a beam. It's bigger than 5. Go to the table and find out number 2. Number 2. It's the bottom line. It's 170. Is 170 bigger than 68? Yes. It's okay. That's it. Takes care of 5.5 shear. Okay? Got a couple more and we've got her whipped. So that's the shear. Equation, problems. Next one is bearing, okay? Hopefully this makes sense. I'm going to try to show it to you here. The equation is relatively simple. Some people can't get the concept. Okay, if you look at the equation in your book, it is on page 209. And this would be our equation. 5.6 is bearing. There's your equation, okay? Okay, what does it mean? Okay, if I have a beam, I'm going to use my book as a beam, and I'm setting the beam on a wall, on another beam, whatever. If I do that, there's going to be a common area between the thing that it's setting on and the thing that's setting on it. So contact area is the mutual area between the members that are sitting and holding. So all you got to do, if you look at it, if I've got a beam right here, let's say I got a beam sitting on a wall. Here's a big concrete wall. The beam comes across, it's sitting on it. It doesn't matter how thick the wall is. That has nothing to do with this. All you need to know is how far on the wall it's sitting. So if you look at that, if I looked at this in perspective, I would have something that looked like this, I believe. The beam would be sitting on the wall. This is the projection onto the wall. That's the amount of bearing. Call that the bearing length. The amount of bearing, the bearing length. That's this right here. Those two are exactly the same. Now, if I know the bearing length, the only thing I have to worry about is how wide is the member bearing on it. So if I looked and